On April 17th, NASA released a set of observations that may mark the beginning of a new chapter in human history. For decades, scientists have searched the skies asking one simple question: are we alone? Now, for the first time, that question feels less philosophical and more scientific. The focus of this discovery is a distant world known as K2-18b. Located 124 light-years from Earth, this planet orbits a small, cool red dwarf star. At first glance, it is just another entry in the growing catalogue of thousands of exoplanets discovered over the past 2 decades. But this one is different. Using the James Webb Space Telescope, astronomers studied the thin layer of gases surrounding this planet. What they found shocked the scientific community. Within the atmosphere, they detected traces of a molecule called dimethyl sulfide. On Earth, dimethyl sulfide is not an ordinary gas. It is produced almost exclusively by living organisms, particularly microscopic marine life such as phytoplankton. It does not linger for long in the air. Sunlight rapidly breaks it apart, meaning it must be constantly replenished. If it exists in large quantities, something active must be creating it. The data suggests that this gas may be present on K2-18b. Even more intriguing, the possible concentration appears far higher than what we see on Earth. Statistically, the signal has reached what scientists call a 3 sigma confidence level. In simple terms, that means there is roughly a 99.7% chance the detection is real, and not just random noise in the data. But science is careful. A true discovery requires a higher standard, known as 5 sigma. Until that level is reached, researchers remain cautious. Instruments can produce errors. Unknown chemical processes might mimic biological signatures. Every alternative explanation must be tested. Still, this is the strongest hint of a potential biosignature ever observed beyond our solar system. If confirmed, it would represent the first real evidence that life exists elsewhere in the universe. As we continue, we will explore what kind of world K2-18b truly is, how this detection was made from unimaginable distances, and what it could mean for the future of humanity. The search is no longer theoretical, it is unfolding in real time. To understand why this possible biosignature matters, we first need to understand the planet itself. K2-18b was not discovered yesterday. It was first identified in 2015 by NASA's Kepler Space Telescope during its extended K2 mission. At the time, it was simply another promising exoplanet, orbiting within the habitable zone of its star. But as the years passed, each new observation added another layer to the mystery. In 2017, follow-up measurements refined its mass and density. The numbers revealed something unusual. K2-18b is about 2.5 times larger than Earth and nearly 9 times more massive. That places it in a category between rocky super-Earths and gas-dominated mini-Neptunes. It is not a twin of our world. It is something different. Then, in 2019, the Hubble Space Telescope detected water vapor in its atmosphere. This was the first time water had been identified in the atmosphere of a planet within a star's habitable zone. Suddenly, K2-18b was no longer just interesting, it was potentially oceanic. The planet orbits a cool red dwarf star known as K2-18. Although it circles much closer to its star than Mercury does to our Sun, the star itself is smaller and dimmer. Because of this delicate balance, the planet receives roughly similar levels of stellar energy to Earth. Temperatures could allow liquid water to exist. Some researchers now describe it as a Hycean world, a term combining hydrogen and ocean. The idea is simple but profound. A global ocean hidden beneath a thick, hydrogen-rich atmosphere. No continents, no visible land. Just endless water under an alien sky. If this model is correct, the environment would be unlike anything in our solar system. The atmosphere would be heavier. The pressure at the surface could be extreme. Sunlight filtering through thick gases would create a dim, diffuse glow over vast oceans stretching thousands of kilometers. This context is critical, because the possible detection of dimethyl sulfide is not floating in isolation. It exists within a world that may already possess water, energy, and stable conditions. The pieces begin to connect, and as we move forward, we will look more closely at how Webb was able to read the chemistry of this distant atmosphere, and why confirming that signal could redefine our place in the cosmos. If K2-18b may truly be an ocean world wrapped in hydrogen, then the next question becomes unavoidable. How can we possibly know what exists in its atmosphere from 124 light-years away? The answer lies in light. Every time K2-18b passes in front of its star, a tiny fraction of starlight travels through the planet's atmosphere before continuing toward Earth. To the naked eye, nothing changes. But to a telescope as sensitive as the James Webb Space Telescope, that passing light carries a chemical signature. Different gases absorb different wavelengths of light. Hydrogen absorbs in one pattern, methane in another. Water vapor leaves its own imprint. When astronomers spread that starlight into a spectrum like a cosmic fingerprint, they can see which wavelengths are missing. Those missing pieces reveal what molecules are present. This method is called transmission spectroscopy. It does not require visiting the planet. It does not require sending probes across interstellar space. Instead, it relies on physics that works the same everywhere in the universe. When Webb observed K2-18b, it detected absorption features consistent with methane and carbon dioxide. That alone was important, but hidden within the data was a more subtle signal, one that matched the spectral fingerprint of dimethyl sulfide. Because DMS is rare and difficult to distinguish from similar molecules, scientists repeated the observations using a different instrument on Webb, one that operates in the mid-infrared range. If the signal were an artifact or glitch, it would likely disappear under different observational conditions. It did not. The signature appeared again. This repeat detection elevated the statistical confidence to what researchers call 3 sigma. In practical terms, that means the probability of the signal being random noise is very small. Still, astronomy is cautious by necessity. 3 sigma is compelling, but it is not definitive. There remain possibilities that unfamiliar chemical reactions driven by extreme temperatures or pressures could mimic the same pattern. The atmosphere of K2-18b is not Earth's atmosphere. Unknown photochemical processes may be at work, yet the fact remains, from nothing more than filtered starlight, humanity has begun to read the chemistry of a distant ocean world. And within that chemistry lies a signal that, if confirmed, could point toward biology. In the next part, we will examine why dimethyl sulfide carries such weight and why its presence would be far more than just another atmospheric detail. The signal detected in the atmosphere of K2-18b would not have caused such excitement if it were just another common molecule. Methane can be produced by geology. Carbon dioxide is widespread throughout the cosmos. Even water vapor, while essential for life as we know it, does not guarantee biology. But dimethyl sulfide is different. On Earth, dimethyl sulfide is produced almost entirely by living organisms. Specifically, it is generated by microscopic marine life such as phytoplankton. When these organisms break down in the ocean, they release this gas into the atmosphere. It is partly responsible for the distinct smell of the sea. More importantly, it is chemically fragile. Sunlight destroys dimethyl sulfide quickly. In Earth's atmosphere, it survives only a short time before breaking apart. That means, if it is detected in significant quantities, something must be actively replenishing it. It cannot simply linger for centuries like carbon dioxide. It requires a continuous source. This is why the possible detection on K2-18b carries such weight. If dimethyl sulfide truly exists there, and if it exists in high concentrations, then some ongoing process must be producing it. On our planet, that process is biological. However, caution remains essential. K2-18b is not Earth. Its atmosphere is rich in hydrogen, not nitrogen and oxygen. Temperatures and pressures may differ drastically from anything familiar. Under such conditions, unknown chemical reactions might generate molecules that resemble dimethyl sulfide in spectral data. Scientists must rule out every non-biological pathway before drawing conclusions. The current confidence level stands at 3 sigma, roughly a 99.7% probability that the signal is real. But real does not automatically mean biological. It only means the molecule may be present. To claim life, researchers must reach 5 sigma certainty and demonstrate that no plausible abiotic chemistry can explain the observation. This careful approach is not hesitation. It is the strength of science. Extraordinary claims demand extraordinary evidence, and the discovery of life beyond Earth would be the most extraordinary claim in human history. Yet even within that caution, something has shifted. For the first time, we are not merely speculating about distant microbes. We are analysing data that could, if confirmed, point directly toward biological activity on another world. In the next chapter, we will explore what life on such a planet might look like, and whether an ocean beneath a hydrogen sky could truly support living systems. If dimethyl sulfide on K2-18b is eventually confirmed to have a biological origin, the next question becomes inevitable. What kind of life could survive on such a world? As we discussed, this planet is likely not a rocky Earth twin. It may be a vast ocean world wrapped in a thick hydrogen-rich atmosphere, with pressures and temperatures very different from those on our planet. There may be no continents, no forests, no familiar landscapes, just a global ocean stretching thousands of kilometers in every direction beneath a dim alien sky. On Earth, life began in water. The earliest organisms were microscopic, simple, and resilient. They survived in extreme environments long before complex plants or animals existed. If life has emerged on K2-18b, it would almost certainly follow a similar path, beginning with microbes. But these would not be ordinary microbes. They would need to tolerate high atmospheric pressure, possible temperature extremes, and a chemistry dominated by hydrogen. Instead of relying on oxygen and sunlight as most life on Earth does, they might depend on chemical reactions for energy. On our own planet, extremophiles living near deep-sea hydrothermal vents survive by oxidizing chemicals such as hydrogen sulfide. They thrive in darkness under crushing pressure. A comparable system could exist on K2-18b. If volcanic or hydrothermal activity occurs beneath its ocean, chemical gradients could provide a steady energy source. In that case, sunlight would not be required. Life could exist entirely in darkness, powered by chemistry alone. If evolution continued for millions or billions of years, more complex organisms might arise. In a dim environment, vision might not be the dominant sense. Creatures could rely on detecting vibrations in the water, sensing temperature differences, or responding to subtle chemical signals. Some might even produce their own light through bioluminescence, similar to deep-sea species on Earth. The thickness of the atmosphere and the density of the ocean would influence body structure. Organisms might develop flexible but strong outer layers to withstand pressure. Their forms could be elongated, drifting slowly through deep waters, or compact and adapted to stable thermal regions. Of course, all of this remains speculation. We do not yet know whether life exists there at all. We do not know its chemistry, its metabolism, or whether it resembles anything familiar. But if dimethyl sulfide truly signals biology, then somewhere beneath that distant hydrogen sky, living systems may already be thriving. In the next part, we will examine the remaining scientific uncertainties and why reaching absolute confirmation is far more complex than it may seem. Speculation about alien oceans and drifting life forms is fascinating, but science cannot rely on imagination. Before anyone can claim that K2-18b hosts life, the evidence must survive the most rigorous testing humanity can apply. As mentioned earlier, the current detection of dimethyl sulfide stands at 3 sigma confidence. That means the signal is statistically strong, but not yet definitive. In physics and astronomy, discoveries require 5 sigma. At that level, the probability of error becomes extraordinarily small. Reaching that threshold is not about skepticism, it is about precision. To move from possibility to confirmation, researchers must answer 2 critical questions. First, is dimethyl sulfide truly present in the atmosphere? Second, if it is present, can it be produced without life? The first question demands repeated observations. The James Webb Space Telescope will continue to monitor transits of K2-18b, gathering more spectral data. Each new transit refines the signal. Noise decreases, patterns become clearer. If the molecular fingerprint of dimethyl sulfide remains consistent across multiple independent measurements, confidence will steadily rise. The second question is even more challenging. Scientists must model every plausible chemical pathway that could generate the same spectral signature. K2-18b's hydrogen-rich atmosphere may allow reactions that do not occur naturally on Earth. High pressures, intense radiation from its red dwarf star, or unknown photochemical cycles might create similar molecules abiotically. Computer simulations, laboratory experiments, and atmospheric models will all play a role. Researchers will attempt to recreate K2-18b-like conditions and test whether non-biological chemistry can produce dimethyl sulfide in large amounts. If such pathways are ruled out, the biological explanation grows stronger. There is also debate about the planet itself. Some scientists argue that K2-18b could be more like a mini gas giant than a true ocean world. If it lacks a defined liquid surface, the environment may be far less stable than current models suggest. Determining the planet's internal structure is therefore just as important as analysing its atmosphere. This process will take time, months of observation, years of modelling, careful peer review. Extraordinary claims require extraordinary evidence, and the discovery of extraterrestrial life would redefine biology, astronomy, and our understanding of our place in the cosmos. For now, the data remains promising, but incomplete. Humanity stands at the edge of a possibility, not yet a revelation. In the next part, we will step back from the technical details and consider what such a discovery would truly mean for us, for science, and for the future of exploration. If the evidence for life on K2-18b is eventually confirmed, the impact would extend far beyond astronomy. As we concluded in the previous part, the scientific process demands patience, repetition, and absolute certainty. But imagine that certainty is finally achieved. Imagine the data reaches 5 sigma. Imagine every non-biological explanation is ruled out. What would that mean? For the first time in history, humanity would know that life is not unique to Earth. This would not be a blurry photograph or an unexplained signal. It would be chemistry, measurable, repeatable, verified chemistry in the atmosphere of another world. Biology would no longer be a singular accident confined to one planet. It would be a cosmic phenomenon. Such a discovery would reshape multiple fields at once. In biology, it would challenge the idea that life requires Earth-like conditions. If organisms can survive beneath a hydrogen-rich atmosphere on a distant ocean world, then the range of habitable environments expands dramatically. Planets once dismissed as too extreme might suddenly become viable candidates. In astronomy, it would alter the search strategy for future missions. Telescopes would prioritize similar Hycean worlds. Spectroscopic surveys would focus more intensely on subtle biosignatures. Funding, research, and global collaboration would accelerate. The search would shift from wondering if life exists to mapping where it exists. Philosophically, the change would be even deeper. For centuries, humans have looked at the night sky and projected myths, hopes, and fears onto distant stars. Confirmation of extraterrestrial life would transform that sky into something more intimate. Not empty, not silent, but inhabited. It would not necessarily mean advanced civilizations. The life on K2-18b, if present, might be microscopic. It might resemble early Earth billions of years ago. Yet even microbial life would prove that biology can emerge independently more than once in the universe. And if it can happen twice, it can happen many times. There would also be a humbling effect. Earth would no longer be the sole cradle of life. Our planet would remain precious, but it would be part of a much larger biological story unfolding across the cosmos. The question would shift from "are we alone?" to "how common is life?" and eventually to "how far has it evolved elsewhere?" For now, we stand in a transitional moment. The evidence is promising, but not final. Humanity is waiting, watching, calculating, and as more data arrives, the possibility that began as a faint spectral signature may become one of the most important discoveries in human history. In the next part, we will explore other worlds that are also considered promising, and how K2-18b fits into the broader search for life beyond our solar system. As we consider what confirmed life on K2-18b would mean, it is important to remember that this planet is not the only candidate in the search for habitability. Over the past 2 decades, astronomers have identified more than 5,000 exoplanets. Among them are several worlds that, while very different from Earth, may still offer conditions suitable for life. One such planet is TOI 700d, located just over 100 light-years away. It orbits within the habitable zone of its small red dwarf star and receives slightly less energy than Earth does from the Sun. Models suggest that if it possesses a stable atmosphere, liquid water could exist on its surface. Unlike many red dwarf planets, it may not be fully tidally locked, meaning it could experience a regular cycle of day and night. Another intriguing world is Kepler 1649c. Slightly larger than Earth and positioned within its star's habitable zone, it receives about 75% of the light that Earth receives. Although it is likely tidally locked, climate simulations indicate that a temperate region could exist along the boundary between its permanent day and night sides. In that narrow twilight zone, stable conditions might allow water to remain liquid. These planets expand our understanding of what habitability might look like. Not all life-bearing worlds must mirror Earth exactly. Some may orbit smaller stars, some may have thicker atmospheres, others may rely on greenhouse effects to distribute heat across their surfaces. Compared to these candidates, K2-18b stands out because it does more than sit in the right temperature range. It presents a potential biosignature within its atmosphere. That distinction elevates it from theoretical possibility to active investigation. Yet the broader search continues. Each newly discovered world adds context. Some are scorching gas giants, others are frozen mini-Neptunes. A few, like those in this growing list, appear balanced on the edge of habitability. Together they form a cosmic laboratory, offering clues about how common life-friendly environments may be. As telescopes become more powerful and data more precise, the catalogue of promising worlds will continue to grow, and within that expanding map of distant planets, K2-18b remains one of the most compelling chapters in a story that is still being written. In the next part, we will turn to some of the strangest exoplanets ever discovered and explore how extreme diversity across the universe reshapes our expectations of what a planet can be. As we expand our search beyond promising ocean worlds and temperate planets, we begin to see a deeper truth. The universe is not only capable of producing life-friendly environments, it is capable of producing extremes far beyond anything found in our solar system. Some exoplanets orbit so close to their stars that their surfaces glow like molten metal. On certain ultra-hot giants, temperatures climb above 2,000 degrees Celsius. Metals such as iron do not remain solid. They vaporize into the atmosphere. Powerful winds then carry that vapor to the darker side of the planet, where it cools and condenses. In effect, iron rain falls from alien skies. Other planets are defined not by heat, but by structure. Astronomers have identified gas giants surrounded by ring systems so vast they would dwarf Saturns. If one of these planets were placed in our own solar system, its rings would dominate the night sky, stretching from horizon to horizon. There are also planets so young and hot that they glow with unusual colors, including faint shades of pink or magenta. Their light does not come from reflected starlight alone, but from the lingering heat of their own formation. These worlds remind us that planets are not static objects. They evolve, cool, contract, and change over time. Perhaps most surprising are planets with densities so low they have been compared to cotton candy. Despite being similar in size to Jupiter, they possess only a fraction of its mass. Their extended atmospheres are puffed up by heat, creating enormous diffuse spheres of gas. Together, these discoveries reshape our expectations. A planet does not need to resemble Earth to exist. It does not even need to resemble the familiar categories of rocky or gaseous. The diversity is staggering. This context matters for one important reason. If the universe can create iron rain, planet-wide ring systems, and worlds lighter than foam, then it can likely create environments we have not yet imagined. Somewhere within that diversity, biology may arise under conditions that challenge our assumptions. K2-18b is part of this vast spectrum. It is neither the strangest nor the most extreme world discovered, but it may be one of the most significant, because among all this cosmic variety, It is one of the few where the chemistry hints at something alive. In the final part, we will return to the larger question that connects all these discoveries and consider where humanity stands in this expanding universe. After exploring ocean worlds, iron rain, vast ring systems, and planets lighter than foam, we return to the quiet signal that started this journey. A faint chemical fingerprint in the atmosphere of K2-18b, a possible trace of dimethyl sulfide drifting beneath a distant hydrogen sky. Throughout this documentary, we have moved from discovery to analysis, from imagination to skepticism, from possibility to caution. We have seen how light travelling across 124 years of space can carry within it the chemistry of another world. We have examined how that chemistry might point toward life, and why science refuses to declare victory too soon. Now, we stand at the edge of something larger than any single planet. For centuries, humanity believed Earth was the centre of everything. Then we learned it orbits the Sun. Later, we discovered that our Sun is only one star among hundreds of billions in the Milky Way. Today, we know there are billions of galaxies beyond our own. With each step, our sense of uniqueness has grown smaller, but our understanding has grown deeper. If K2-18b ultimately proves to host life, it will mark the next step in that progression. Life would no longer be a rare miracle confined to one fragile world. It would be part of the cosmic pattern. Biology would join gravity, chemistry, and physics as something that emerges naturally when conditions allow. Even if the signal fades under further scrutiny, the search will not end. The tools we have built, the telescopes we have launched, and the methods we have refined are only improving. Future observatories will analyze atmospheres in greater detail. New missions will expand the catalogue of habitable candidates. Each year, the map of the cosmos becomes more detailed. The question, "Are we alone?" is no longer philosophical. It is experimental. It can be tested with data, spectra, and mathematics. Somewhere among thousands of stars, another world may already be alive. K2-18b may or may not be the first confirmed example, but it represents a turning point. For the first time, humanity is not just looking outward in wonder. We are reading the atmospheres of distant planets and finding hints that life could exist beyond Earth. And as we continue to observe, calculate, and question, one truth becomes clear. The universe is not silent. It is waiting to be understood. Whether K2-18b holds life or not, the search itself is transforming us, expanding our perspective, and reminding us that our story is part of something far greater than we once imagined.